computer that controls the sort of off-the-shelf Hummingbird autopilots. It has 260 megahertz ARM processors, 3 MEMS, gyroscopes, accelerometers. They perform all the state estimation and attitude control at a kilohertz, which doing it that fast really improves the stability of the vehicle and is one of the key enabling technologies that allowed the Aztec vehicles to be so stable. And finally, the onboard computer provides a serial interface to the main computer that we showed earlier, which allows us to pull out the filtered IMU output and provide the control input over the stereo. In addition, we have, it takes the RC, standard Berg RC receiver at 72 megahertz, which we can use to, at the flip of a switch, just take over and have fully manual flight, just like a regular RC helicopter. In addition to that, for the competition, we mounted an emergency kill switch, which uses a 2.4 gigahertz Spectrum RC receiver, which is connected to, which has its own voltage regulator and is connected through an AVR processor directly to the power FETs of the motors, which allows us to just directly kill the power to the motors with the flip of the switch on a separate 2.4 gigahertz transmitter. So that was our vehicle, and with this capable vehicle that's able to sort of maintain steady attitude, hover in one, it's not going to flip over on us, but it will drift around and won't stay in one place without external corrections. We turn to our job of estimating the position in real time, for which we mainly use laser-based scan matching to do this. And in developing our system, we found that we really needed a multi-level system hierarchy to accomplish the full task from the low level all the way to the very high level. So the different modes of the helicopter have different requirements in terms of their speed. So controlling the attitude of the quadrotor requires very fast, very high bandwidth control. That's being done at a kilohertz on board. Controlling the position is still needs to be fast, but it can be an order of magnitude less. So that needs to run at about 10 to 40 hertz because the quadrotors are sort of underdamped, not passively, they're passively stable in attitude, but not in position. We need to make sure that we're getting very high rate, accurate state estimates in real time. And then at the very top layer, we are trying to close loops, perform simultaneous localization and mapping to sort of build maps of the environment and figure out where the vehicle is in the environment on a sort of global scale so that we have sort of the full stack. And it would be nice, and people have tried to just use the SLAM directly in the sort of position control loops to stabilize the vehicle, but as far as we've been able to see, the SLAM algorithms today just aren't fast enough to be incorporated in sort of the real-time control loops. And so having this clean separation between the sort of real-time position control and the sort of global consistent mapping is very important. One sort of convenient thing in developing this sort of large system with so many interlocking processes that they all communicate over standard IP using the lightweight communication and marshalling library that was developed for MIT's entry into the DARPA Grand Challenge competition. It uses UDP multicast and makes it very easy to communicate in between all processes. As other teams mentioned, working in MATLAB is very convenient, and it's got bindings for C, C++, Java, Python, MATLAB. So it allows you to easily get data in and out of, between all these languages, and it's very convenient to work with. And as a sort of add-on from that, it made it very easy for us to switch out our sort of core sensing modalities. So as I mentioned before, with the stereo cameras, we're able to perform visual odometry to estimate the position of the vehicle. And so everything between the sort of gray line on the left and the right is sort of somewhat separated. So we can plug and play different position measurement sensors. So we can switch between the stereo camera and the visual odometry, or the laser scanner and the scan matcher. And since they're publishing the same messages, the rest of the modules, you can just reuse the same sort of, or we can reuse the same sort of higher level logic to do the sort of whole data fusion and mapping in a sort of sensor independent way. So a little bit about the laser odometry. This is a video that shows sort of the real-time view of what the laser is seeing at any one time. It's looping right now. And so we see that the environment's moving. These little points right here are actually the height beams. So the helicopter was flying at roughly a constant height. And so the job of the scan matching module is to take a laser scan and basically find the optimal rigid body transform between the current scan and previous one. So take the laser range scan. First thing we do is we extract these sort of line segment polyline contours in the same way that, also I should note that our algorithm is based on the work by Ibn Olson et al. In 2008. And so we extract these polyline contours. We then use those contours to make a sort of a cost map that shows the likelihood of seeing a laser reading. And then when we get a new scan, we try all possible combinations of matches between the current scan and that likelihood map in a sort of brute force search over a small window, which provides a very robust measure of the motion. And we do all that at 40 hertz with sub-centimeter accuracy. So you can do that even though you are doing a brute force search if you're smart about the window that you search over and the way that you do that search using sort of vector operations to sort of do whole windows at a time. You can do it very fast. Similarly, or somewhat similarly, if we're trying to do this, get the same relative information out of the stereo vision, the first task is to do feature detection in both the left and the right image. You then have to find the feature correspondences by tracking between the left and the right frame. And that allows you to do a depth reconstruction and get this sort of 3D point cloud for the current one. Then when you get a new frame, you track and match the features between the current frame and the previous one, which allows you to figure out where these sets of features should move. You do the depth correspondence between the two new frames again, and then you have these two 3D point clouds, and you can use standard least squares or whatever optimization method you want to sort of correspond and find the optimal motion that allows you to reconstruction the environment. Finally, that provides a somewhat noisy measurement. Errors over short times add up. And so we use a sort of windowed bundle adjustment method to sort of integrate and refine those feature and pose measurements over time. These are standard visual odometry techniques that you can actually go read some vision papers on visual odometry. And so once we have this sort of local position information, the vehicle is able to sort of hover in one spot, explore. With a 30-meter range, we can explore like a room this big. But if we want to do something like explore the first floor of this data center at MIT, I know the map looks like it's just totally messy, but that's actually how the floor plan looks. So you have to sort of take a longer time view of doing the mapping. But fortunately, you can use sort of 2D algorithms developed for ground robots. For example, we use the open source G-mapping SLAM algorithm by Grizzetti et al. To integrate the laser measurements over time using the odometry that we get out of the scan matcher, and we're able to build sort of large-scale maps. So once we have these maps, the next technical challenge was to sort of do the autonomous planning and exploration to actually complete the mission. So this is the FSM of the, or sort of general flow as we go through the mission. So we take off, we perform a window scan, then, go into the window scan now. So we scan to build a 3D point cloud. Basically, as we move the helicopter up, we get a very dense 3D point cloud of the window.